All right, so in this lecture, we're going to start with electric charge and electric forces. Hope everyone is familiar with these concepts. Electric charge, right? We know that there are two types of charges in nature. We call them positive and negative. The names are totally arbitrary, okay? And then we also know the forces between them. Like charges repel and unlike charges attract, okay? And it's actually very easy to do an experiment using things around us to demonstrate the electric forces between charges. That's why I said that I hope everyone is familiar with this electric charge and electric forces. So there are also like a lot of interesting ways to test, to demonstrate electric forces between charges. Okay, my favorite demo in this part is this one. So I'm going to show you this. I'm going to do it now. I'm going to come to the front. So all you need is going to be some Scotch tapes. Okay, so if you have some Scotch tapes at home, you can even do this experiment yourself. It's very cool. So what I'm going to do is this. I'm going to make a pair of tapes, okay, and I'm going to charge them, okay, with updated charges, and then I'm going to test the forces between these tapes, okay. So I just made one. I pressed it onto the table. Now it sticks to the table, right? So I'm going to call it bottom because I'm going to place another one on top of it. I'm going to label it with the letter B to remind myself this is the bottom one. Now I'm going to place another one on top of it, right? Okay, press it onto the bottom one, and now I'm going to label this with the letter T, okay? So I know this is the top one. Now there's a smart way to charge them actually. Take them off and then separate them very quickly. Okay, so this is the top one and this is the bottom one, okay? All right, so they're already charged. So what I'm going to do is this. I'm going to make another pair. And I'm going to charge them the same way. So in this case, the bottom and the bottom, they should have the same charge, right? And top, they should have the same charge. So I can test forces between these four of them, right? So I can, well, I don't know, I'm not sure what type of charge the bottom carries, the top carries, but that's fine. They would carry the opposite charges, okay? So now I'm gonna take them off, quickly separate them. Now this is the bottom one. So if I put bottom close to bottom, well, you see that I can't even put them together. There's definitely a repulsive force between them, okay? There's a definite repulsive force between them. Now if I put bottom and top together, they would attract each other, right? So that's that. Now I'm going to use this top one. So you see that the top and bottom, they would attract each other, right? And top, they will repel each other, right? See, there's a repulsive force. I can't even put them together, okay? And top and bottom, they would attract each other. Okay, so this is a very nice demo, my favorite demo in this part, to show the forces between different types of charges. Of course, as I said, we don't know which one carries negative, which one carries positive charges, but the names are totally arbitrary, right? If you like, you can call them top and bottom charges, right? Or up and down, or left and right, right? Okay, so that means if you can charge things with the same type of charge, you put them together, negative and negative, or top and top, they should, negative and negative, or positive and positive, they should repel each other. If you charge them with opposite charges, top positive and negative, they would attract each other, right? Okay. Then how can we charge things so easily with just objects around us, okay? So it's actually very easy to understand using the structure of an atom. Okay, I hope everyone knows the structure of an atom. So an atom, it's made of a nucleus and electrons orbiting the nucleus, right? So inside the nucleus, there are protons and neutrons. Okay, protons carry positive charge. Neutrons don't carry any charge. That's why they're called neutrons. Okay, and the electrons carry negative charge. Okay, so the electrons, and then you see that the force between the protons and electrons, right, should be attractive. So the electrons, they always feel a force toward the nucleus, toward the center, right, when they're orbiting. And then that agrees with the centrifugal force theory we learned in physics 1, right? Anything in circular motion must have a centrifugal force toward the center, always, to keep them in a circular motion, right? And this centrifugal force can be any force. Centrifugal force is not a new type, a special type of force that comes only from a certain agent, okay? It can be any force, right? And we have seen that in physics 1. Friction, normal force, tension, gravity, any force can be centrifugal. And sometimes it's a combination of several forces to be the centrifugal force, right? In this case, electric force is the centrifugal force, right? Without this attractive electric force between electrons and protons, electrons, they cannot orbit the nucleus. So atoms wouldn't be able to form at the beginning, okay? So we wouldn't even be around, okay? So, and then these electrons, they can orbit the nucleus at different orbits, okay, at different layers, okay? So they can occupy different orbits, okay? So, and then some of the electrons, if they are in the outmost orbit, right, we call them outer electrons, okay? And these outer electrons, because compared to these electrons close to the nucleus, the force between them is going to be the weakest, right? So these electrons are very easy to be transferred from one atom to another atom, right? So if you rub two things together, okay, what you're doing actually is just that you transfer some electrons from one material to another material. So the material that loses electrons behaves positively charged, right? The second material that gets actual electrons behaves negatively charged, okay? So that's how you can get things charged. You can test the forces between them, okay? So, and then the charge on so as I said, the proton and neutron, proton and the electron, so the only difference between them is the sign of the charge they carry. They actually carry the same amount of charge, okay? And that's called the fundamental charge. That's the smallest free charge in nature, okay? The charge on a single electron or single proton, okay? So you cannot find any charge smaller than that in nature, okay? So the fundamental charge, what is the amount of the fundamental charge? The charge proton or electron carries, that's a very small number in SI units, okay? So the SI unit for charge is the Coulomb, okay? In honor of Coulomb, who discovered the law of electric force. We're gonna see that in a minute, okay? So, and the symbol we use for electric charge is Q, okay? So you can write the charge of something is like 10 coulombs, okay? It's pretty much like you write a force is 10 newtons. So Q is the symbol we usually use for charge. And sometimes we use big Q, small q. And C is Coulomb, is the unit. So the fundamental charge, the amount of charge a single electron or proton carries, it's a very small number, okay? In SI units, it's 1.60 times 10 to the negative 19th coulombs. Okay, so that's the fundamental charge. So that's a constant. Okay, you don't need to remember any constant. Okay, and then charge is conserved, right? So that's what we when we separate these two tapes. Okay, one tape it's going to become positive charge. another tape is going to become negative charged. Okay, they always carry opposite charges because you're not creating any charges in this process. You're just transferring, in most cases, electrons from one object to another object. Right? So if one object gets positive charge, the other object is going to get negative charges. Okay, and they would carry the same amount of charge. Okay, all right. So when we charge things around us by rubbing them together, usually, we are always doing what we are doing is just separating charges. Right? We're not creating charge in this process. It's totally a charge separation. Okay. And I attached a link to a YouTube video, very good video, that explains this charge separation in our life. So take a look at the video, okay? Very nice video. So that's the forces between different types of charges we just discussed. There's another thing, very interesting thing you can do. You can also do an experiment, okay? It's called electric polarization. Electric polarization. Remember, what we said is that you have two things charged. You can test the forces between them, right? Like charges repel, unlike charges attract. So the force can be repulsive or attractive, depending on what type of charge they carry. But you can also do an experiment, okay? Again, you can use things around you to do that experiment. To show that if you bring a charged object to a neutral object, okay, and then you can also see attractive, and it's always attractive forces between them, okay. Again, there are different, a lot of interesting, cool experiments you can do to demonstrate that. We're going to do one of them here. So, but what is happening between this charged object and a neutral object? How can How come there is an attractive force between a charged object and a neutral object? Take a look at the image, okay, on this slide. Okay, say if you bring a positive charge to a neutral object, a totally neutral object on the right, take a look at the image. So the positive charge is going to attract these negative charges in this neutral object, right? So it's not going to be able to separate these charges because the force is very weak, but it's going to pull these negative charges a little bit closer to it. It's going to push these positive charges a little bit farther away from it, right? So the negative charges, they will have attractive forces with this positive charge, right? External positive charge. And these positive charges inside this neutral object, they will have repulsive forces between this external positive charge, right? So if these two forces cancel out exactly, then you shouldn't see any force, right? But because the atoms are polarized, so all these negative charges, they have been shifted a little bit closer to the positive charge. So all these attractive forces added together, they're going to be a little bit larger than all the repulsive forces added together on these positive charges, right? So at the end, you will see a net attractive force between this positive charge and the neutral object, okay? So, and it doesn't matter if the external charge is positive or negative, right? If it's negative, then everything is going to be, it's going to attract the positive charge and then push this negative charge, right? Okay? So, but anyway, you would always see the force between this charged object and the neutral object attractive. Okay, because it always attracts the opposite charges a little bit closer to it. Okay, so this is called electric polarization. These atoms, they are polarized, okay, in the same direction, almost in the same direction. Okay, so that there's a net attractive force between the external charge and the neutral object. Okay, so but these charges, they're not separated, right? If you remove the external charge, then all these atoms, they're going to be aligned randomly. So all these forces are going to cancel out. All these, okay. So again, as I said, there are different ways to demonstrate this force. So again, my favorite demo is this. A soda can, empty soda can. You need to use an empty soda can. So next time, after you finish a soda, okay, save the can. You can do this experiment yourself. It's very cool. Empty soda can, and then you use a rod. So of course, there's no interactions between them. right? There's no interaction. There's no way you can move this soda can using this rod until you hit it, right? But I can do that without touching the soda can. I can actually move this soda can using this rod, okay, by using the attractive force, okay, after electric polarization. So what I'm going to do is that I'm going to charge this rod first, right, by rubbing it against the cloth, okay? So once I get this guy charged, okay, so there will be a attractive force between, you see, the soda can and the rod, okay, because now I can polarize the atoms in this empty soda can so that all these object charges, they're going to be a little bit closer to this rod, okay? And then if I remove all these charges, okay, on this rod, then this force is going to disappear because they are both neutral. There's no electric force between them, right? Nothing, okay? So it's very cool. You can also do that at home, okay, yourself. All right, so that's electric polarization. Remember, this is different from two charged objects, right? This guy is charged. You're going to charge one of them, but another one is neutral. Then the atoms are polarized. You can see a net attractive force between them, okay? And that's why you can also use this rod to attract like a lot of small bits of paper, okay? All right. All right, so that's all conceptual, quantitative, okay? But remember, what physics does is that to make numerical predictions, very precise predictions, explain experiments, right? So in order to do that, you need a theory. You need equations, okay? Don't hate equations. Without equations, there's no way you can make quantitative, precise predictions. You can only explain things very quantitatively, okay? Very quantitatively, okay? So, and then the law, as I said, was discovered by Coulomb, right? So that's why we call it Coulomb's law, okay? So the law is this. The electric force between any two charges, okay, is proportional to the product of these two charges and the inversely proportional to the distance, square of the distance between them, okay? And then this Ke is a constant. In SI units, it's a very large number. Okay? So that's the Coulomb's constant. We call it Coulomb's constant. So when we use this equation, okay, remember I didn't put an arrow on top of this force. So that means this is only the magnitude of the force. And that's why I use an absolute value sign here, okay, to make sure that everything is positive, because the charges can be both positive or negative. But when I use this equation, I only use this equation to calculate the magnitude of the force, right? Because the force is a vector. Okay, if you want to know all the information about the force, you will need to know the magnitude and the direction. Okay, and the direction is tricky, right? Usually, I don't use equation to. I don't really want to like to use an equation to figure out the direction. What I usually do is just draw an arrow based on some facts I already know, and then if I do want me to describe this direction, I would pick a reference axis and then tell you the angle between this vector and the axis, right? That's how we specify the direction in physics, okay? We don't just say, oh, it's pointing this way or that way, okay? First of all, we draw it out, right? And then I can pick a reference axis and tell you the angle, okay? So what we do, if I want to find the electric force between two charges, the first step, I would use this equation to find the magnitude, right? Just put all the numbers in, make sure everything is positive, and then get the number, right? Now the direction. If I want to figure out the direction, remember that like charges repel, unlike charges attract, right? So I'm just going to use that fact to draw arrows on these charges, right? For example, if I have two positive charges like this, okay? So what is the force between them? Repulsive. What is the direction? Well, it's hard to describe. I would draw it out for you. So the force, like this is Q1, this is Q2. The force from 2 on 1 is going to be in that direction, right? And the force from 1 on 2 is going to be in this direction. Okay? And if you really want me to describe the direction to you, I would set up like an axis, like X or Y, and then tell you, oh, it has an angle like 30 degrees with the positive X, things like that. Right? That's how we specify direction in physics. All right? But first of all, I would draw them out based on the fact that like charges repel, unlike charges attract. Okay? So when I use Coulomb's law to find the force on the charge, I would always do that in 2 steps. Use this equation, put all the numbers in, make everything positive, find the magnitude. And magnitude is always going to be positive, right? And then if I want to find the direction, I use the signs of these 2 charges and then draw these arrows. And you can see that F1 and F2, first of all, they should have the same magnitude, right? Because if you calculate the force from F1 on 2 and F2 on 1, you would get exactly the same numbers, right? And the direction, opposite. So these 2 forces, they're equal and opposite because they are action and reaction. And which law is that? Newton's third law, right? You see, everything is consistent in physics. All the laws we learned in physics 1, they're still true here. That's why we call them laws, okay? So we're going to still use a lot of laws, concepts, skills, techniques we learned in physics 1 in this class. So you can't just forget everything we learned in physics 1, okay? And also vectors, we're going to be dealing with the vectors a lot in this part. Okay, so that's Coulomb's law. Now, and sometimes if you read a different book, you may see a different form of Coulomb's law. So sometimes they write this constant as 1 over 4 pi epsilon naught. Okay, and then the rest is going to be the same. So this epsilon naught is also a constant in physics. We're going to see this constant again in Gauss's law, I believe. Okay, so this is 8.85 times 10 to the negative 12 Coulomb squared over Newton meter squared. Okay, so of course if you compare, well, remember they're the same law, they're just in different forms. So that means the Ke and the 1 over 4 pi epsilon naught, they should be equal, right? Okay, so that's the connection between these 2 constants. This epsilon naught is called permittivity of free space. Okay, excuse me. All right, so if you read a different book or if you read any resources from the internet, right? When you see this, don't freak out. This is still the same law, right? Just different form. Okay, right? So it's still Coulomb's law. Okay. Now let's take a look at the first question in this part. Okay, so this is usually the first question the professor does in electric charge and electric force. This is a very classical problem. Okay, so we're going to do this problem and I'm going to tell you why we are interested in this. Okay, so let's first take a look at this question. The electron and proton of an hydrogen atom are separated by a distance of approximately 5.3 times 10 to negative 11th meters. We want to find the magnitude of the electric force between them, okay? Well, first of all, we know the force is going to be attractive, right? Because the electron and proton, they carry opposite charges, so the force will be, because the proton is positive, electron is negative, right? Okay, magnitude, well, I'm just going to use this equation, right? Put all the numbers in, you can find the electric force. Now, Ke is a constant. The distance problem gives you, right, the constant, no, not constant, the number. Q1 and Q2, well, proton and electron, as we said, they carry the same amount of charge, this E, right? The only difference is that proton, we call the charge on proton positive, the charge on electron negative, by convention, okay? So if I say Q1 is the proton, that's the number I plug in, right? And Q2 is the electron, that's the number I plug in, okay? But in this case, if I'm just calculating the magnitude, I don't even need to worry about sign, right? Because I already figured out the force is going to be attractive, okay? So you can just plug all the numbers in, find the force between the magnitude, right? And don't forget the square here, okay? Every time there are people making this mistake, this is a very common mistake people make, they forget the square, okay? Okay, I can't do iClicker with you, but I still want you pause the video, do the algebra, okay, solve the problem with me, okay. You learn better if you do that with me instead of just watching me do that, okay. So pause the video and then do the algebra and see, and then compare your answer with mine, okay, see if you get the right answer, all right. Now, if you plug all the numbers in, so the number I got, the electric force between them, it's 8.20 times 10 to the negative 8 newtons. All right, so this is, of course, is a very small force, right? Because we're talking about the force between an electron and proton, right? So it's going to be a very small force. So the next thing I want you to do is this. I want you to find the ratio of the electric force to the gravitational force. Remember, we learned the theory of the universal gravitational force, right, in physics 1. Any two objects, if they have mass, there's always attractive force between them, and that's universal. That was discovered by Newton. Okay, so in this case, there are two objects. They have mass, right? So there will be an attractive gravitational force between them, right? You can calculate that. What is that equation? That's the equation we learned in physics 1, right? If you still remember that. Big G times M1, M2 over R squared. Okay, take a look at these two equations, right? Do you notice anything? Of course, they're exactly the same form, right? A constant times the product of two properties divided by the distance squared. This R is the distance, okay? So this is called inverse square law, okay? So it turns out the gravity and the electric force, they both obey this inverse square law, okay? Is that a coincidence? We don't believe so, okay? If you look at these two equations, say you don't know what these symbols mean. You don't know what big G means. You don't know what M and Q means, right? You don't know what KE means. You look at these two equations, you would say, they look the same equation to me, right? It's just like someone wrote the same equation with different symbols. I don't really see the difference, right? So that's what I usually say, right? Physicists believe there is a complete theory for this universe, right? Which should include everything, okay? And nature has already given us a lot of hints, okay, on that. Like this is one of the hints, right? By looking at these two equations, I can't believe that there's no connection between them, right? So I believe there must be a complete theory that you can, where you can unify gravity and the electric force, okay? So, but interestingly, we haven't found that theory, okay? Okay, you may guess that, okay, you know, that's a lot of this, it's so obvious, right? These two forces, they have the same, these two equations, they have the same form, so they must be connected, right? So we haven't found the theory, okay? Like physicists are still trying to find the theory, but we still, we already unify the electric force and magnetic force, as we're going to see at the end of this class, okay? That was done in the 19th century. So that was a big step in the history of physics, okay? So, and then, as I said, if you believe someone created this universe, right? So they must have created this universe using one theory. That's beautiful. A totally beautiful, complete theory, right? They're not going to use 1,348 theories to create this universe. That's going to be stupid, right? That's going to be stupid, okay? But we are the product in this universe, right? We are the product of these laws, and we are trying to understand, okay? We're trying to uncover this complete theory. So we're making progress, but we haven't reached that yet, okay? And I believe someday we will be able to find the complete theory, okay? All right, but anyway, so that's gonna be the equation used to calculate the gravitational force between them, right? And this big G is a constant. So this big G in SI units, it's gonna be a very small unit, a very small number. All right, so in order to find the gravitational force, well, at the end we want to find the ratio, right? But you're going to first find the gravitational force between them, right? So then you're going to need the mass of the proton and electron, right? They're constant. You can look them up. I'm going to write it here. Okay, so that's the mass of proton. That's the mass of electron. And the distance is going to be the same, right? They are still 5.3 times 10 to the negative 11th meters apart. So put all these numbers in. Again, pause the video, do the algebra. Put all these numbers in, find the gravitational force between them, and then divide them to find the ratio, okay? Then we're going to see which force is larger, okay? All right, so let's see. So the number I got for the gravitational force is 3.61 times 10 to the negative 47th newtons. Okay, now divide them. What do you get? You will get 2.27 times 10 to the 39. Okay, so what does this mean? This means the electric force, okay, even though it's very small, okay, 10 to the negative 8th. But if you compare that with the gravitational force between the proton and electron, right, it's so huge, right? It's 10 to the 39 times larger than the gravitational force between the proton and the electron. Okay, so why is this a big deal? Why are we doing this? We're comparing two, like, extremely small forces. This is a big deal because that's actually makes our life easier when we study this elementary, and when physicists study these elementary particles, right? So when you study these elementary particles, especially if you want to study their motion, their behavior, you need to figure out all the forces on them, right? So electric force, you need to include that, and a magnetic force, as we're going to study later, okay, you include that. Do you need to include gravitational force? In principle, yes, because the gravitational force is still there, right? So, but when you compare them to the EM interactions, they're just negligible. You don't need to include them, right? You don't need to worry about them, the gravitational force at all, because it's just too weak compared to the electric force and magnetic force, okay? Even if you want to consider, okay, so that's the gravitational force between the proton and electron. What about the gravity of the proton and electron themselves, right? If you do an experiment on the Earth, the electron and proton, they have their own gravity. Well, even if you want to consider that, right? Like for the proton, what is the gravity? Its own force of gravity, its weight, it's going to be m times g, right? So m is this number, okay? 9.8, g is 9.8, so it's almost 10. So you're going to get approximately 1.67 times 10 to the negative 26 newtons, right? And the electron, what about the weight, the mg? Well, that's going to be this number multiplied by 9.8, which is almost 10. So it's just going to give me almost 9.11 times 10 to the negative 30 newtons. Again, compare these two numbers with this electric force, okay? So that means if you want to study these elementary particles, okay, you're going to consider the electric force between them, magnetic force between them, gravity from the Earth or between them. No, don't worry about the gravitational force at all. Like, it doesn't matter it's come from each other or from the Earth, because they're just too weak compared to EM interactions. So gravity is actually much, much weaker than EM forces. Okay, the reason we feel gravity from the Earth is because the Earth is so huge, right? So the gravitational force is always attractive. So that means if you consider the force, gravitational force from between you and the Earth, then that's going to be significant, right? What about the gravitational force between you and the things around you, right? You don't feel that. right? You don't feel that, right? We also did the calculations in physics 1. So, and this is a big deal. This makes our life easier when we study the behavior of the fundamental particles, right? You don't need to worry about the gravitational forces, okay? And that's also true when we study like the even the objects in macroscopic scale, right? Think about it. If I do an experiment here, a car moving on a track, right? I want to study its velocity, acceleration, energy, momentum. So I would need to draw all the forces on it. So I would draw its own gravity, normal force, friction, tension, things like that. But in the meantime, it also feels the gravitational force from everything in this room on it, right? It's going to feel the gravitational force from me. It's going to feel the gravitational force from the marker, the solar cane. But do I need to draw them on this cart when it's moving on a track? No, I don't. We never did that in physics 1. Why? Because these gravitational forces are totally negligible. If you compare them with the normal force, its own gravity, and then tension and things like that. So that's why we don't need to worry about, even though there might be like hundreds of other gravitational forces on this cart moving on this track, I don't need to worry about them. I can just focus on these like 3 or 4 or 5 forces. Makes my life easier, okay? So it's the same deal here, right? In microscopic scale, if you deal with these elementary particles, you can totally forget about the gravitational effects, okay? You can just focus on the E&M interactions or other, interactions that dominate in microscopic scale, okay? So that's what I usually say. Nature has already been very kind to us, very, very kind to us, okay? All right, so that's why we wanted to do that, and this is always the first problem, like the professor solved in this part, okay? Compare the electric force and gravity. Okay, actually electric force is much, much greater than gravity, right? So that's why we can set up an experiment in real life to test the electric forces between objects. Very easy, right? Can you set up an experiment to test gravitational forces between these two guys? No, there's no way you can do that because the gravitational force between these two guys, it's so weak. Okay? All right, so that's this question. Now let's take a look at the next question. Okay, so we just learned this equation. So if we know the things on the right, we can put them in and then solve for the force. But sometimes we don't need the force, right? We know the force, but we can rearrange this equation to find anything on the right? So for example, I can find Q1 or Q2 or the distance even, okay? So that's what we want to practice in this question, okay? A small class B has been charged to 18 nanocoulombs, okay? Nanocoulomb is just 10 to the negative 9th. A small metal ball bearing 2.5 centimeters above the bead feels a 0.037 Newton downward force, electric force. We want to find the charge on the ball bearing, okay? So I have 2 charge objects, okay? I'm just going to call them a Q1 and Q2. I don't care what they are, what they're called, right? It's like when we have things moving in physics 1, we have a problem. I'm just going to call them M1 and M2, right? Okay? Now, let's draw it out. So, the 2 charge objects, I'm going to call them Q1 and Q2, and then let's say call this a small glass bead Q1. Okay, so this guy has a charge 18 nanocoulombs, positive, right? So Q1, 18 nanocoulombs. Okay, and there's a charge above it. We don't know, that's actually what we want to figure out, right? Feel the force downward. So that's the force from 1 on 2, 0.037 newtons, right? And of course we know the distance between them is 2.5 centimeters. Okay, if you want to use this number, convert it to meters. We want to find the charge on the ball bearing, so we want to find Q2. Right? Okay, so let's see. First thing I can do is this, right? Rearrange this equation and then plug numbers in, find Q2, right? Because we know the force between them, K is constant, distance given, Q1 is given, right? But you should be careful. When you rearrange this equation, because everything is positive, in this equation, we make everything positive. So when you rearrange this equation, you will only get the absolute value, the magnitude, okay, of Q2, okay? You don't get the sign, okay? Say if you get 5 coulombs here, you only get the magnitude. You don't know if it's positive or negative yet, okay? You just don't stop there. If you stop there, there's 50% chance you get it right, 50% chance you get it wrong. Because it can be 5 or -5. It's going to make still everything correct, right? So then how do I figure out the sign? Again, we use the force and the other charge to figure it out, right? It's like when we figure out the direction of this force, we use the fact like charges repel, unlike charges attract. Now we're going to still use that fact to figure out the sign of one of the charge, okay? I want to know the sign of Q2, right? What is the sign of Q1 positive? Q2 feels the force from Q1 toward Q1. Is this force attractive or repulsive, right? That's going to help you figure out the sign of Q2, right? Because if it's attractive, that means they should carry opposite signs, right? If the force is repulsive, they should carry the same sign. That's how I figure out the sign. So always 2 steps, right? When you use this equation, everything is positive, okay? You don't get any sign, you don't get any direction. Once you finish that, you're going to use the fact like charges repel, unlike charges attract to help you figure out the direction or signs, okay? So now let's do that, okay? Again, pause the video, do the algebra, figure out the sign, see if you can get the right answer, all right? So if you rearrange that equation, what you're going to get is this, right? Force times r squared divided by KE and the absolute value of Q1. Everything is positive. Now you can put numbers in, right? You know the force between them, the distance converted to meters, KE constant, Q1 converted to SI units, right? So at the end, you will get 1.43 times 10 to the -7 coulombs, okay? If you stop here, as I said, you may get it right, okay? And you may get it wrong, right? Because you haven't figured out the sign, right? You only figure out the amount of charge is going to be this, okay? Is it positive or negative? Take a look at the sign of Q1, right? Q1 is positive, and the force from Q1 to Q2. So Q2 feels the force then. Q2 feels the force to pull it, trying to pull it toward Q1. So that's attractive, right? So Q1 is attracting Q2. Of course, in the same time, Q2 is also attracting Q1 upward, right? But we are only interested in this force, and this force is down, so this is attractive, okay? All right, so that means Q1 and Q2, they should carry opposite signs so that they attract each other. So whatever this number is, Q2 must be negative. All right, so it's going to be negative 1.43 times 10 to the -7th coulomb. So that's the right answer. Okay, so I'm going to stop here for this lecture.